Brian Retford, co-founder and CEO of RISC Zero. So let's welcome Brian.
Check. Hello, everyone, and good morning. Yeah. So today I'm going to be talking about where did my clicker go? ZK at the limit, and specifically, we're going to be talking about proving entire optimism epochs. So I want to give a quick intro to the RISC Zero ZK VM. Hopefully, everyone here knows what ZK is. Is it good? Maybe. Okay, I left the ZK intro out of this deck, so I guess you'll just have to keep up. So RISC Zero is a zero-knowledge virtual machine, which means that it proves the correct execution of any program written in Rust right now, but really anything that can compile down to RISC-V. So in the ZK context, the circuit is the RISC-V chip, and the inputs are whatever your inputs are, and also the program that you're running. And run all this through the RISC Zero ZK VM, and you get a nice, succinct proof of correct execution that you can do things with. So it's pretty easy to get started with RISC Zero if people haven't actually played around with it. It's not much harder than cloning a repo, running a couple cargo commands, and then you can really start proving anything that that exists in Rust. So let's see, how long ago was this? 6 months ago, I think Optimism put out a mission request, an RFP effectively, for figuring out how to ZKify Optimism. We submitted a response for that, and were selected to actually build this. So what this looks like from our perspective is actually taking existing Rust code, proving it, and then extending that to also prove all of the additional semantics of Optimism. So with Zeth, the first Type 0 ZK EVM, it was actually the first Type 1 ZK EVM that I'm aware of. We actually just built this on top of, as you can see, REVM, Alloy, and Ethers. What this actually let us do is build an entire ZK EVM with only about like 5% of the additional sort of code change over the existing code base. So, building on top of that, Optimism is like quite a bit more complicated than ETH. So, we, as part of this mission, we ran a bunch of Optimism blocks through this OP Zeth process, and you can see there's a whole bunch of interesting metrics, such as the number of ZK cycles per gas, which is something that varies up and down as you'd expect, but is also kind of more consistent than you'd expect. We'll get into sort of how all of this works in a second. So anybody can check out and use Zeth. You just got to clone the repository here. And it's pretty simply laid out, and we're going to go over just a little bit of how all of this works. Zeth has this very handy CLI that you can use to build blocks, run the blocks, so you can actually create the blocks that you're about to prove them, and then verify them. And we support Ethereum, Optimism, and the Optimism-derived network. So if you just want to play around with Zeth to actually build these blocks, you can use the CLI to connect to an RPC provider, and it will go through the modified Zeth code and spit out these blocks for Optimism or for Ethereum. The code for these sort of bits of block building are pretty simple. We had to modify several parts of the actual RETH system in order to make them ZK friendly. But once that was done, you can see that there's not really a ton of code that actually has to run inside ZK in order to build these ZK proofs of correct Ethereum execution. So the OP architecture, it's obviously a full L2 on Ethereum. The DA ends up on ETH proper. So every transaction on OP can actually reference DA from Ethereum, which greatly complicates the process of proving any of these sort of optimism blocks. Rather than just needing to look at the transactions on ETH, you actually have to effectively build a coprocessor that can look at these transactions on ETH, prove things about Ethereum, and then roll them up into a single proof for optimism. Yeah, so the core architecture is pretty simple. We just use these existing crates that I mentioned earlier. There's a custom Merkle Patricia tree we had to write in order to sort of get the data flow between the host of the ZKVM and the guest to be a reasonable size. So this is just a bunch of code that one can look at to see how this sort of all comes together. Effectively, a lot of this process of building these optimism blocks has to be coordinated across several actual simultaneous ZK programs that are running at the same time. So the block proving flow for optimism. Effectively, you build the blocks natively, not using any ZK, just talking to a regular RPC node. We log everything that happens, and then get storage proofs for all of the actual access to the L1, retrieve the historical block headers. We build this new in-memory DB, and then we actually build the block in ZK and produce the proof of correct block construction. Yeah, and I guess the one, see, this is going to go back. No. Yeah, the one detail there is that we use the RPCs to sort of build up this memory database, and then inside the ZK VM, obviously we're not making network requests. We're just dealing with this database that we've already built up. So the L1 to L2 derivation process is how Optimism scans these L1 DA transactions and then is able to use that data to prove the correct execution of the Optimism transactions themselves. So the RISC-0 ZKVM, two of the, I would say, major innovations we made over the last year was recursion. I mean, this is not that major inside the ZK space, but our recursion is very fast. And we also added the ability to chunk up an arbitrarily large proof into many small chunks so they can be parallelly proven in parallel. Separately, you can also take a proof that has been generated and verify that inside a new guest program. This effectively allows you to, you could think of multi-thread your ZK program. So in the context of Optimism, we can start proving one block, and then we can launch a bunch of threads that will go out and separately prove all of these bits of Ethereum DA, and then we can use composition to bring them all together. So this is just a visual example of the way the sort of continuations process works. So if we're just building an Ethereum block, you know, we might split up the proving computation into about, who knows, like 4,000 segments. We actually can vary the sort of size of the segments based on the memory available on a particular machine. So you can tune the size of these segments that you then use recursion to collapse into a single succinct proof using recursion. And then, of course, once you do that, you can also have all these programs that are also running massively in parallel alongside each other that then all get combined using this guest mode composition, resulting in one final proof. And then you can do this, of course, Optimism has this concept of epochs, which are a whole bunch of blocks that eventually get posted to Ethereum. They usually, I think, contain about 1,800 blocks. So we then again use composition to create these proofs of epochs. But as you can see, the guest code for doing this kind of composition is also pretty simple Rust. There's a little more of color there. Obviously, if you're interested in this, checking out the source code repository and playing around with it is the best way to actually understand what's going on. Yeah, and summary from this sort of OP mission, we were able to actually roll up 180 optimism blocks correctly, and I think this is probably the biggest general purpose ZK program that's ever been run, clocking in at about 190 billion cycles. As you can see, the times are not like the most encouraging, let's say, but there's a ton of optimization to be done there, and we really expect these times to dramatically decrease over the next couple months. And we could go into a lot of detail about how exactly that will get done, but there's inefficiencies across the entire system, but certainly adding acceleration circuits for things like Ketchak will be a big part of doing that. Yeah, so what are we going to be doing in the future with Zeth? We're going to make it faster, more chains, and full validity proofs for entire rollups. An exciting aspect of this approach is that you can, rather than, Polygon built an amazing ZK EVM, spent a lot of money on it, but say upgrading to Dankun is going to be complicated. So when you're building ZK EVMs by using the source code that already exists, you have the, ease of keeping up with what's going on in Ethereum in general. But then if you actually want to experiment with changing how some of these VMs work, this framework gives you a way to do that, and a way that we've effectively proven can scale to the most complicated kinds of VM transactions in the space. Yeah, that's actually all I have. Do people have any questions? Yes, sir. Yeah, there's no reason. So the RISC-0 ZKVM is completely zero knowledge. So you could build an EVM. Like, you could actually prove, if this were efficient enough, you could actually prove to Flashbots that you had some bundle, for instance, that contains certain properties without revealing anything using this exact same kind of code base. Yeah. Yes.
What's the number of transactions per second you can do this way, and do you think about other exploration?
Yeah, so let's see. The number of transactions, it varies widely based on how many GPUs you're using. Right now, these numbers were all from like 300 node cluster, but there's, we're expecting like a 10x improvement, just because we really focused on trying to get the broad set of parallelization done. So all of this composition and recursive systems, rather than the exact nature of the hardware acceleration. So yes, there's a lot of room for improvement in the GPU kernels, and yeah, we expect to see that pretty soon. Our goal, I think, is to get to somewhere where we could actually be proving these roughly in real time by the end of the year. Well, you can definitely prove some things on a phone. But I mean, like, if you wanted to prove, so say like passports and everything now have these, digitally signed identities in them. If you wanted to scan that and create a proof that, I don't know, you were a Capricorn, or that you're over a certain age or something, you could do that on your phone, and I think that would, minute, 30 seconds. So pretty practical, I think. Yeah, so that's actually tunable by this sort of segment size parameter that we have. So we tend to set it to just 1 megacycle, so 1 million cycles is a segment, but the memory requirements are directly influenced by how you set that. So at 1 million cycles, I think we're at like 8 to 12 gigs of memory. So you can readily target consumer cards, but if you do want to scale that down, you can. You're just inducing more recursion overhead at the end of the day. Yes?
What if time of under application and data, like what kind of data availability or bandwidth needs are needed for the verification?
Yeah, I think just anything that you would normally need to run a validator node is nothing beyond that. So you just, oh, that's a good question. I don't know. Rami, do you know? Yeah, like how long does it take to get all the data to do this? I assume it's pretty quick from whatever RPC provider you're using. Oh, I see. I think I misunderstood what you were saying. Yeah. Yes, yes. Whatever. So the final succinct proof that represents all 190 billion cycles is milliseconds to verify. And actually, I mean, we spit out a Stark proof, but we also have a system to take that Stark proof and convert it into a Snark proof, which you can then post on Ethereum mainnet, and that will. Well, it's on Sepolia right now, but we will be launching it to mainnet very soon. Yes. I think there's some recent papers that came out that show that if you rely on certain conjectures that you can have some compounding effects there, but generally no if you construct it right. Yeah. Yes.
Yeah, so you mentioned like you have to fork a number of wires using like alloy and things like that. Like what's the kind of story around that? I'm assuming there's some reasons which are probably performance and then some other reasons why you have to fork them.
Yeah. So I don't think the forks were too. I think Rami actually did most of the work here. So. Right, but I think we did end up building this custom Merkle-Patricia tree, and that mostly has to do with just making sure that we can get memory over from the host side to the guest side in the most efficient manner. Like, I think it's used like a zero copy structure. Right, yeah, everything expected to talk to like an RPC node or something like that.
If I was writing like a proof, I guess my question is like would I, like if I want performance, I'll have to maybe use something, but like otherwise I could just use.
Yeah, you should generally, like I think the development flow we have in mind is you just start with the program that you actually want to run, and then see if the performance is acceptable. And then if it's not, we have a bunch of patched crates that use the sort of big int accelerators that we have, and we'll have more and more accelerators available, and the ability to write your own accelerators in the future. So you can, go as deep as you want to on the optimization front, but the idea is you should be able to prove out like the possibility of what you're doing, in a day or whatever. Yes?
Beyond like roll-up proofs, what other like heavy verifiable computation like use cases that would require hundreds of millions or billions of CPUs are you guys thinking about?
There's been a couple. We actually have proven bootstrapping for TFHE, and that takes about a billion, I think, cycles right now, although that could be pushed down a lot. So similarly, we just did a proof of speedrun of Doom that I think, about 30 frames a second if you don't render, actually. So it's actually pretty close to being able to prove the state transitions of Doom in real time. I don't know how much of a use case that is, but yeah. What's that? Yeah, so right now, the way floats are supported is through, so we support the one flavor of RISC-V right now, RV32IM, which is integer with a multiplier unit. So all of the float is soft float put in by LLVM. So it's not great, but it does work. But the next version, we have a much fancier mechanism for doing this. All right, I don't see any more hands. So thank you, everyone.